let's turn our attention to the normal distribution, another one of our specific probability distributions that we'll cover in this block of our quantitative business analysis course. Just to set our frame of reference, again, we are in our module on probability and distributions, and we've talked about probability distributions in general, and in this block we're focusing in on some specific distributions. We've spoken about the binomial distribution already, and now we're turning our attention to the normal distribution. And this distribution, unlike the binomial distribution or the generic discrete probability distributions that we talked about previously, is a continuous probability distribution. And to set our, our frame of reference for this conversation, recall our histogram as a frequency distribution. It's a graphical representation of a frequency distribution. We had bins or intervals on our horizontal axis, and then we have columns, the height of which represented the frequency. In reality, if you recall, it was actually the area of these columns, of these vertical rectangles, that actually represented the probability of being at that value. This, again, is for a case that we made categoric in our histogram, and the same would hold if we were thinking about a distribution of a discrete numeric variable. So if we then convert these frequencies via relative frequencies to proportions, this becomes a graphical representation of the probability distribution. Now, as we go from discrete or categoric intervals down towards something continuous, what effectively happens is that the size, the width of each bin becomes smaller and smaller. And if we've got a large enough data set that we could smooth out the noise sort of shown here in all of these up and down fluctuations around this general shape that we're seeing, and we take this down to the ultimate case of having a very, very infinitely small step size, which is the case for a continuous distribution, we end up with a probability distribution curve that looks like this smooth line drawn in blue here. And we can contrast that with our original very granular discrete case. So again, the continuous probability distribution is looking at infinitely small step sizes. Remember, our definition of continuous variable is one where there were no gaps in the possible values. So the distance between one value and the next higher possible value is infinitely small. Okay, so with that in mind, let's take a look at this normal distribution. And the blue curve that I've represented here is actually a normal distribution curve. And what do we know about this curve? It's a continuous probability distribution, as we've said. It's symmetric and unimodal, so there's a single peak to this distribution, and it rolls off evenly on either side. And in reality, the normal distribution is really a family of distributions. There are actually an infinite number of possible normal distributions, and each one of these distributions is specified by its location and shape, which are determined by the mean of the distribution and the standard deviation of the distribution. And let me see if I can give you a bit of a visual representation of this by taking a look at this little graphic applet here. And what we're seeing here is a curve for a normal distribution. And as the mean of that distribution shifts, we can move this distribution to any possible value, or we can have normal distributions that have any possible value for the mean. Just depends on what it is the variable is measuring. In addition, the spread of this distribution can also change. So in this case, what I'm doing is I'm narrowing the standard deviation, the spread of the distribution. So the specific normal distribution that I'm referring to can be specified uniquely by the values of the mean and the standard deviation. And of course, I'm showing you here standard deviations going from very small numbers, from about 0.5 up to a value of 1 on this scale. But of course, the standard deviation could go much larger and much smaller, down to effectively a standard deviation of 0, which would imply that all the values fall exactly at one point. So I guess theoretically we would not call that a normal distribution, but again, the standard deviation can go down to very, very small values and up to very large values, just depending on the variable that's being measured. Okay, so one of the things that's very powerful about the normal distribution is that a very large number of natural phenomena follow this distribution. And that makes it very powerful for us to understand. And we talked back in the early days about symmetric distributions and symmetric histograms. And when we were first talking about that distribution, some of the terms that came up, that came to mind when we thought of a symmetric distribution were things like a normal distribution or Gaussian distribution. And these are specific examples of symmetric distributions. As a matter of fact, in the case of the normal distribution, it is a symmetric distribution, but it's one in which the height of the curve, based on how far away you are from that peak, varies with according to a very, very specific formula. So those are the things that define a normal distribution as a very specific distribution. Okay, well, let's dig into a little bit more information regarding this normal distribution. As we mentioned, it's a normal distribution is one of a very large family of distributions, and it turns out there's a specific normal distribution that is often used to represent other distributions in this large family of distributions, and this is called a standard normal distribution. It acts in a way as a template for all the rest of the distributions. It's a normal distribution that has a mean exactly at 0 and a standard deviation of 1. And it turns out we already know a lot about the standard normal distribution from our discussions of symmetry and of probability in general. And just to point that out, I'll ask you, what's the probability? If I know I have a variable that's distributed according to the standard normal distribution, what's the probability that the value of this variable is less than 0? We could ask also, what's the probability that x is less than 1? What's the probability x is greater than 1? All of these are things that if we think back to our thoughts about symmetry, and if we think back to our ideas about the empirical rules based on standard deviation, we can think through these things. And again, I'll use this applet to illustrate. This is, again, a normal distribution, and I've put in a value for the mean at 0 and a value for the standard deviation at 1. And what I'm showing here in red is the proportion of this distribution that has values less than 0. And as you can see, we get a probability of 50%. That should make sense because we know that the normal distribution is symmetric, and if the mean is at 0, then the probability of being less than 0 should be half of the distribution. What about the probability that x is less than minus 1? Well, how could we estimate that? If we think about our empirical rules, what did we say about the probability for a symmetric distribution of being at a value between minus 1 and plus 1 standard deviations away from the mean? Well, supposing I go from minus 1 to plus 1, and I'll show this here, and this is the area we're talking about, between minus 1 and plus 1. We said this was 68% roughly. Okay, well, what we're asking in this problem, though, is not the probability of being between minus 1 and plus 1, but being less than minus 1. Sorry, less than plus 1. So this entire shaded area from negative infinity, theoretically, up to a value of 1. But based on what we know about our empirical rules, we can figure this out. If the probability of being between minus 1 and plus 1 is 68%, then the probability of being between 0 and plus 1 is half of that, or 34%. And if we add that to our probability of being less than 0, which is 50%, we get a total of around 84%. And it turns out for the actual theoretical normal distribution, the standard normal distribution, the probability is a 0.8413, so just a bit over 84%. So our estimate from our empirical rules would actually have done a really good job here. What about the probability that x is greater than 1? Well, it would be the area that's not shaded on this curve, and we know that the sum of the probabilities from minus infinity to plus infinity has to equal 1. Therefore, the probability of being between a plus 1 and a very large value, so greater than 1, is going to be right around 16%, 1 minus 84%. And theoretically, it calculates out to 15.87%. And we'll take a look at doing those calculations very exactly now to get these sort of numbers, and not just using our empirical rules, which we said were an approximation. So again, we know a lot about this distribution already. Now we might also ask, well, where does most of this standard normal distribution lie? Roughly all of it is going to fall in what range of values? Well, again, from our empirical rules, we know that almost 100% of the distribution falls between plus and minus 3 standard deviations away from the mean. And for a mean of 0 and a standard deviation of 1, that would imply values between a minus 3 and a plus 3. And actually, just to give you a visual on that as well, here's what it looks like. It's almost 100%, but not quite. So if I were to show you here from minus 3 to plus 3, we can see there's a very small unshaded portion on either side in the tail, either tail of the distribution. But virtually all of the distribution falls between minus 3 and plus 3. If you went out to, minus 3.5 and plus 3.5, again, you're up to 99.95% of the distribution. So you get an idea as to where, for any normal distribution, where the bulk of the data, virtually all of the data, is going to fall within plus or minus 3 to plus or minus 4 standard deviations away from that mean. So if you know the mean and you know the standard deviation, then any point that's more than 3.5, 3, 4 standard deviations away on either side, it's a very significant outlier, a very rarely occurring value. Okay, I will return to that applet a little bit later on to take a look at some other questions. But let's go on and talk about the relations in the family. How do we relate things back to the standard normal distribution? It turns out that we can really do any probability calculation for a normal distribution based on what we were just doing with our empirical rules. And the standard normal distribution allows us to transform any normal distribution into something called a z-distribution. We can find a value on the standard normal distribution that corresponds to any value on any other normal distribution. So if we have a normal distribution and we know mu and sigma, and we have a particular value in that distribution, we can calculate where that value would roughly fall on the standard normal distribution, and then intuitively we can use our empirical rule ideas to get at least a ballpark idea as to where that value falls in the original distribution. So for a normal random variable x, where we know mu and sigma, we can calculate a z value. And it's calculated as the deviation x minus mu. So how far away is our value from the mean of the distribution that it belongs to, divided by the standard deviation. So deviation, x minus mu, divided by the standard deviation. And what we're really saying is, okay, how far away is this, not in absolute terms, but in numbers of standard deviations? Is it 1 standard deviation away? Is it a minus 2.5 standard deviations away from the mean? And this value is going to be returned as this z value. And this can be very useful for us. In Excel, there's a formula that lets us calculate this z-value, and it's called the standardize function. And we put in our value of x, we put in the value of mu and sigma for that specific normal distribution, and it will return the z-value. Frankly, I find it just as easy to type this formula into Excel as it is to type the word standardize, but they do exactly the same thing. Now, what does the z-value tell us? Like I said, once we get that z-value, it's going to be a number that will tell us directly how many standard deviations x is away from the mean and in what direction. Because if the sign of the z-value is negative, it means that x is below the mean. So that numerator in that expression was negative. If the z-value is positive, it means that x is above the mean. So if I had a z-value of 1.5, that means, hey, my x value is 1.5 standard deviations above the mean. And this is a useful thing for us to know because, again, then we can apply our empirical rules very intuitively around those numbers. We can get an idea as to, hey, is this an outlier or not? Is it a fairly typical value in this distribution, etc. Another benefit, again, for the z-transform is that it lets us map different normal distributions kind of onto the same scale. We can compare different distributions and get a sense for where certain values fall. And we'll see an example of this in a short while. We're going to take a look at a problem out of your textbook, and we'll see how the z-transform actually helps us to do some calculations around around certain distributions. Okay, so just a couple of conceptual things. Would a z-value be a measure of relative standing? True or false? Again, if we think about what that z-value does, we'd see that the answer should be true, right? The z-value tells us where a given value falls in its own normal distribution. So it tells us how many standard errors it is above or below the mean, and based on our empirical rules, we can calculate roughly what proportion of the distribution falls below that value or above that value. We can do that using our empirical rules, or as we'll see shortly, we can do that very accurately using some functions in Excel that actually essentially do the calculus for us in calculating the area underneath that normal distribution curve. Can we use the z-values to calculate probabilities and percentiles? Yes. Well, as I was just saying, once we have that z-value, we can use it, again, either through empirical rules or through our direct calculations to find the probabilities that fall to the left or to the right of a certain value. And we can also, if we know a certain cumulative probability or a certain percentile, and it's useful to know when we think about our probability distributions like this, the cumulative probability has the same effect as a percentile, right? If the percentile value is the value that has a certain cumulative probability falling to the left of it. So the percentile value would effectively be the z-value that corresponded to a certain probability falling to the left of it. And we'll see an example of this shortly as well. Okay, let's take a look at calculating probabilities, cumulative probabilities in Excel for a normal distribution. For a specific value x of a normal random variable, if I know x and I know the mean and standard deviation of that distribution, the cumulative probability, that is the probability of being at or below that value of x, can be calculated using this formula in Excel, norm dist for normal distribution. And there are four arguments. One is the value itself of x that I'm interested in, looking at the cumulative probability up to, the mean and standard deviation of this normal distribution, and then the last parameter is actually this cumulative flag. And for the case of the normal distribution, we're always going to leave this on for probability calculations. We're always going to set it to 1. And we'll talk about that in just a minute, because that's a very important distinction from the binomial distribution, for example. If we know that we're dealing with the standard normal distribution, so we know that mu equals 0, sigma equals 1, then we can put in 0 and 1 respectively into the normdist function in Excel, or we can use a new function called normsdist. And we put that S in there to imply standard normal distribution. And then we don't need to put in the 0 and the 1 for the mean and standard deviation. And we don't need to put in that cumulative flag on the end. All we can need to do is put in our value of X, and it'll return the probability of being at or below X. You could also think of this as putting in the value of Z, right? Because if this is the standard normal distribution, which is also called the Z distribution, we just plug in the Z value and it gives us the probability at or below that specific value of Z. Let's take a look now at a problem that exercises these functions, this normdist or normsdist functions. Okay. I've created this example. You don't have a data file for this. I will post this file so you can kind of work along with things. But the scenario here is that we have times for processing expense reports within some accounting department of a company, and we're told that the times are normally distributed, and the mean is 12. And the standard deviation is 1.5. And I haven't put units on here somewhat intentionally. It depends on your company. But let's say there's some automated system that can have work through automated workflow and things like that. And let's say it takes 12 minutes. Let's say the average time is 12 minutes and the standard deviation is 1.5. We want to know the probability that a given expense report is going to take less than or equal to 15 minutes. How would I calculate that? And we'll think back to our formula that we just used. So I've got a normal distribution, mu is 12, sigma is 1.5. I want to know the probability of being at or below a value of 15. So I'd say equals normdist, Normdist, and then I plug in my value of X, which is 15 in this case, comma, my mean, which is 12, and I've labeled that mean in this formula. My standard deviation, 1.5, I've labeled that STDEV. And I'm going to put a 1 here for the cumulative probability because I want the probability of being equal to or less than 15. And I get a probability of 0.9772. And I'm going to pull this applet back in here just to confirm that, if you will. So my mean is 12, my standard deviation is 1.5, and I want the cumulative probability. I'm going to just start at a very low value of 0 up to 15. So the shaded area is the probability I'm interested in. This is the probability of a value of an expense report being processed in 15 minutes or less. And as you can see, the probability that was calculated here was 0.9772, exactly what we got using our normdist function in Excel. Okay, what about the probability that X is greater than 15? Well, if we think about the fact that the total probability under the curve has to equal 1, then I could think of this unshaded area as the probability of X being greater than 15. So I could say 1 minus the value that I got before, or I could retype it. I could say equals 1 minus normdist of 15, comma 12, comma 1.5, comma 1. And I get a value of 0.0228. And these two numbers should sum to 1. And I can confirm that in my little summary bar at the bottom of the screen. Now, right about here is where some students start to think, wait a minute, something's a little squirrely here. Because we asked what's the probability of being less than or equal to 15. That's okay. We asked here what's the probability of being greater than 15. All right, that sort of adds up. But when I did my probability of X being greater than 15, okay, do I have to make any accommodation for the fact that I want greater than as opposed to greater than or equal to. I don't know. It's something I have to think about. Let's look ahead to one more part of this problem, and with that in mind, suppose I want to know the probability that x is less than 10.5. Okay, so I want to know the probability of being below 10.5 in this case. All right, well, it's less than, I can start, I don't have to say 1 minus, I can start out just saying equals norm dist of, and then the question is, what do I plug in here? Do I just say 10.5, comma, 12, comma, 1.5, comma, 1? Well, what would cause me to do something other than that? And we may think back very directly to how we would have handled this if this was a binomial distribution. We'd have said, okay, I don't want to include 10.5 here because we specifically asked for the probability of being less than 10.5, not less than or equal to 10.5. So I don't want to include 10.5, so I need to only include something below 10.5. The point here really is this. In the case of a continuous distribution, okay, if I say I don't want to include 10.5, then I have to step down to the next value that's just below 10.5. Now, if this were a binomial distribution, we might be thinking of stepping down by a whole unit to 9.5 or whatever the discrete element is as we, the step from one value to the next. Maybe it's to 10 or to 9.5 or something of that sort. In the continuous case, though, for a continuous distribution, what's the next smallest value just below 10.5? Well, since it's a continuous variable and not a discrete variable, that next value down is 10.49999999, okay, because it's an infinitely small step from one value to the next. Theoretically, it's a step of only of 0, okay? And this is a point that's very, very important to understand with as a distinction between continuous distributions and discrete distributions in terms of how we have to handle their formula, specifically in Excel. The issue is this: yes, we are going to step down here, but we're not going to say -1. We're not going to say -0.5. We're really going to be subtracting 0 from this value of 10.5. So in reality, we don't have to subtract anything at all. We can just say norm dist of 10.5, comma, 12, comma, 1.5, and we get our value of 0.1587. Okay, and this is it's an important point to dwell on for a minute and get our heads around, because we talk through the binomial distribution in a way. There's some things that we had to be very careful about, how we dealt with being less than a certain value instead of less than or equal to a certain value. And those were important because we had a discrete step size that we had to account for. In the case of a continuous distribution, we don't have that level of restriction on us, and that's something to be, well, it makes life a little easier for us in the calculations, but it's really a point to stress. And let me reinforce in a slightly different way. The difference between x equals or is less than 10.5 and x is less than 10.5 is going to be the value of the probability of x being exactly equal to 10.5. And if we think about this, matter of fact, let me bring back in my my applet here, and we can visually see this. Suppose I want to know the probability of being between 10 and 11. Okay, it's going to be the area of this shaded portion of this distribution. All right, and to calculate that, I would actually integrate this function between 10 and 11, and I would find the area under this curve. This is what Excel would be doing for us. What happens though if I say I want the probability of being exactly at 10.5? I need to think about shrinking this. So let's suppose I'm going to go to from 10.4 to 10.6. All right, well, now I've got something that's really close to a rectangle. I can just take the height of this and the width, and that would be a pretty good approximation, especially if I took the height right at the middle of this little sloped portion. But you see what's happening. The area is getting smaller and smaller. If I ask the question, what's the probability of x being exactly equal to 10.5, I really have to say I want this area starting at 10.5 and ending at 10.5. And you notice it goes away. My rectangle is still there, except it's infinitely small. And this is an important thing to recognize. The probability of being exactly at any value, whether it's 10.5 or 15, so if I go from 15 to 15, being exactly at the mean, for a continuous distribution, the probability of being exactly at any value is always going to be equal to 0. Once we know that, it makes it easier for us to deal with these calculations, because it's exactly the same for me to say, hey, what's the probability of being less than or equal to 15? Or for me to have just said the probability of x being less than 15. So there's no distinction there. All right, so hopefully that's clear. And recognize that's only the case for continuous probability distributions, not for discrete probability distributions. In that case, it's very important for us to keep track of what do we want to keep in, what do I have to subtract, etc. Okay. Now, another interesting point that this brings up is this question of this norm dist formula and this cumulative flag. So what does it mean for me to turn the cumulative flag off in the norm dist function? Because that would imply that I don't want the cumulative probability. I want the probability exactly at 10.5. Right? It would kind of imply that. And we would think that should give us a value of 0. We just saw that on the little Java applet. But when I do this in Excel, I get a number that is not 0. It turns out, and if you look up the help function in the help behind the function in Excel, the normdist function, it turns out that in that function, because they know that the probability of being exactly at 10.5 is 0, they decided to give you a bit of flexibility there. So if you put a 0 in for the cumulative flag, it returns not the area under the curve, not the probability, but the height of the curve at that point, which is something called a probability density. And that may be useful to know in certain circumstances as well, but we don't need it in our probability calculations this way. Effectively, it's the value of the normal distribution function at a given value of x. But we're interested in the area under the curve. So we're for the normal distribution, for the norm dist function, and we'll see this also for the exponential distribution, the expon dist function, we'll always keep this cumulative flag turned on for the purpose of calculating probabilities. Okay, another interesting question is, supposing I want to know the probability of an expense report being processed in somewhere between 10.5 minutes and 15 minutes. Well, how would I do this? And again, we'll use an approach that is should be familiar to us, the same approach that we used in the binomial distribution case. Here I want this shaded area of the curve. And my norm dist function for any value of x is going to give me the probability of being at or below that value. So I'm going to take my larger value, find the probability of being at 15 or below, and then I'm going to subtract the piece that I don't want, probability of being at 10.5 or below. So I'll say in Excel equals norm dist of my larger value 15, comma 12, comma 1.5, comma 1 minus, oh, by the way, it's really important that you spell these things correctly. That should be norm dist with an N. Okay, minus norm dist of my smaller value, 10.5, comma 12, comma 1.5, comma 1. Okay? And you notice here, again, I didn't have to worry about, well, do I want 10.5 or something less than 10.5? Because it's continuous. I can just take the actual boundary values. I don't have to worry about whether they're inclusive, whether they're exclusive. It makes no difference, because the probability of being at 10.5 is 0. The probability of being at 15 is 0. So I mentioned you have to spell these things correctly, right? There we go. So we get a value of 0.8186. And I ask here, is that consistent with our empirical rules? And I'll leave that for you to think about, because if you've been following this, you'll notice that the values I picked here were whole number multiples of the standard deviation away from the mean. So 15 had a z-value of 2, because it's 2 standard deviations above the mean. I'll actually show you on the graph, because they actually showed you here both the z-value as well as the actual x value. 10.5 is 1.5 minutes below the mean of 12, which is exactly 1 standard deviation below the mean, so it has a z-value of -1. So I'll leave it to you to calculate based on your empirical rules once again. This value we get of 0.8186, is that close to what we get from the empirical rules? As you imagine, it should be, but you can just confirm that for yourself. Okay, let's return and talk a little bit more about calculations we can do based on this normal distribution, calculating effectively what I consider to be percentiles. So if I have a normal random variable x, and I know mu and sigma, I can find the value of x such that the probability of being below x is a certain value. So if I know the cumulative probability, I can go back and find the value of x. And that value of x then becomes the percentile value corresponding to that cumulative probability. And the formula that lets me do that is called a norm inverse function. It works backwards from the cumulative probability to the value of x. So I can say x equals norm inverse of, I put in my cumulative probability, my mu and sigma, and it'll return the value of x. Or if I know I have, once again, the standard normal distribution, I say norms inverse. I just put in that s there for standard normal distribution, and then I don't have to put in 0 and 1 for the mean and standard deviation. I can just put in my cumulative probability, and it'll return the z-value in this case. Okay, so let's again take a look at the example of that. Whoops. And how would that fit in? What kind of problem would we really be asking here? Supposing I'm the one who's paid all these millions of dollars for this new automated system, this new ERP system, and I'd like to be able to tell all of my folks who are submitting expense reports, hey, look, 90% of expense reports are going to be processed in less than this amount of time, because it helps me justify all this money I just spent. Well, what would be that number that I could use? That I could say 90% of all expense reports of all values of X are going to be less than a certain amount. Well, I'd be putting in a cumulative probability of 90% from a time of effectively 0 up to some value. And the probability, the area under the curve to the left of that value is going to be 90%. Well, I want to go back and figure out what that value is. And that's where I can use this norm inverse function. So I'll say equals norm inverse. First thing it asks me for is this probability, this cumulative probability, which is going to be 90% or 0.9. And then I put in my mean and standard deviation. I don't have to put in a 1 here. Cumulative flag is not an argument in this function. And I get a value of 13.922, etc. So I could say, hey, 90% of all expense reports are going to be processed in 13.92 minutes or less. So this is how we would use that value. You could also say that 13.922 is the 90th percentile value of this distribution. All right, so this is kind of exercise for us how we can practically use this idea of this z distribution, use the idea of calculating percentile values once I know something is normally distributed, or at least is approximately normally distributed. And it turns out for many, many natural phenomena, like I said, we can model them using the normal distribution or the standard normal distribution as an approximation. And there are certain tests you can do on a data set to determine whether or not it looks like it's from a relatively normal population. And we'll talk about some of those later on in the term. But again, you have these files so you can work along with these and go through them. over and over. At this point, I want to wrap up this segment in terms of our discussion about the normal distribution. And we'll pick up with another pair of very interesting distributions, the Poisson and the exponential distribution, one being an example of a discrete distribution, another being a continuous distribution, and the two of them have a very unique relationship to each other that we'll explore in the next discussion segment.